All right, so welcome to week 4, AI504, and today we're going to talk about autoencoders. 네, 안녕하세요. Hopefully, so last week we had the class replaced by the video from last year, so I hope that everybody watched it. And as I said in the class, we did a Q&A session, but only 3 people showed up, so I hope that's a good sign that only 3 people showed up because all the other 390 other people completely understand what's completely follows the material so far. So hopefully that's a good sign. Right. So today's topic, latent. Before we go into autoencoders, we're going to talk about latent representation. So we in the previous session in the logistic regression neural networks, we briefly talked about latent representation, where we talk about the I'm going to mute everybody.
Oh, yeah. Sorry.
Right. So as I said, in the previous session, we talked about latent representation, where we have the pixel, the image, it compressed into 4-dimensional space, where that 4-dimensional space is used again for the finally predicting whether the image is a male or a female, right? So, but that was only a brief description of the latent representation. So we're going to talk about it in a little more depth today. And then we're going into autoencoders, and then training process. This probably a lot of you are already kind of familiar with this, but we're going to talk about the training process a little bit more in detail, just in case. And then visualization and autoencoder variants, if we have time. So latent representation. So in the previous session, as I said, okay, I'm going to have to mute everybody again. All right, in the previous session, the logistic, after we talked about logistic regression, we introduced another hidden layer on top of the logistic regression to make it a multi-layer perceptron, right? So MLP. And so the setup was that we have a certain resolution. For example, let's say that this is 28 by 28. I think that was the proper the example that I gave, and the total number of pixels will be 768, and then we have the input as 768 dimensional input, and then that is compressed into 4-dimensional space here. So because there are 4 hidden neurons, so that would become a 4-dimensional hidden space. And we were assuming that maybe semantically the first dimension could be such, for example, like does the image contain a long hair, or does it have a mustache, or does the image include a ribbon on the hair, or does it or does the person in the image wear a makeup? So semantically, we could imagine things like this. So because things like these, like having a long hair, or having a mustache, or having a ribbon, or having a makeup, would be beneficial, would help us determine whether the image is a man or a woman, right? So that was our assumption. And we would call that a 4-dimensional latent representation. So this 4-dimensional space is the latent representation space for this image, So because the original image lives in the 786, 768. Actually, yeah, 786, right? So sorry. So the original image lives in the 786 dimensional space. 784. Wait, we can, so 28 by 28. Oh. Yep, it's 784. Oh, okay, that is true. Yeah, sorry about that. So 784 dimensional space is compressed into this 4-dimensional space, and this becomes a latent representation. So once this image is compressed into the 4-dimensional space, then that becomes the latent representation of the original image. And that latent representation, this space, actually, I could use a pointer. Yeah, okay. So this space is trained by maximizing the accuracy of classifying the image into a man or woman, right? So this for example, one image, this image could be transformed into four-dimensional space like this. Maybe another image could be transformed into four-dimensional space like this. And obviously, these two images would have a different value in the four-dimensional space, right? So, for example, this could be their value here, and this image of Alan Turing would be completely different from the image of a woman. And so this could be seen as a mapping function between a original 784. Okay, I wrote it correctly here. So original space, which is 784, and a four-dimensional space, and there's a mapping function between the two. So whatever sample you give from this 784 dimensional space, any image could be Michael Jackson, could be Marie Curie, Alan Turing, Che Guevara, Kim Jong-un, whoever, or even like completely dark image, completely white image, doesn't matter. As long as you give a sample from the 784 dimensional space, then this function will be able to map it to a four-dimensional space, and each sample would be mapped to a unique different sample, right? I mean, sometimes it could be mapped to the same dimension, like almost similar. Nothing could be exactly the same because this is a continuous space, right? But could be mapped to a very, very similar position, for example, because we're collapsing 784 dimensional space into four-dimensional space. So something must be bound to be close in the latent space. For example, like, I don't know, maybe this guy and this guy could be mapped to a very similar value. I mean, we wouldn't know because we wouldn't be able to assume it, but it could happen because we're collapsing 784 into four-dimensional space. So there's a lot of information lost. So something's gotta bound to be in the proximity, right? So we are still talking about the four-dimensional space, and if we were assuming that this four-dimensional space consists of these semantically familiar concepts, such as whether the image has a long hair, mustache, ribbon, makeup, then we could assume that, I can't draw a four-dimensional space, but in the three-dimensional space, at least, one axis could be whether it has a long hair, another axis could be whether it has a ribbon, another axis could be whether it has mustache, and maybe another axis could be whether it has a makeup, So in that space, that space would be semantically familiar space. So how do we learn this space? As I said, there's a mapping function that maps between the input space, which is 784, and the output space, which is four-dimension. How did we learn this space? And the answer is by minimizing the cross-entropy loss. So the task was image classification, whether the given image is a male or a female, right? So by maximizing, or actually, we could say by maximizing the log likelihood, or maybe minimizing the negative log likelihood, which is the same as minimizing the cross-entropy loss. That's how we train that neural network. That's how we trained this entire neural network, by minimizing the cross-entropy loss. And that is how these parameters 1, 2, 3, 4 parameters, and this entire matrix, which would be 784 by four-dimensional matrix, all these parameters are trained, which is by minimizing the cross-entropy loss. So as you can see, this matrix here, which is 784 by 4, that is the mapping function between the 784 dimensional space into four-dimensional space. And since the parameters here are trained by minimizing the cross-entropy loss, we can say that this space is trained or learned by minimizing the cross-entropy loss, which is the same thing, right? So before we move on, actually, I can show you a very, very nice visualization from a website, which is right here. Was there a question from Chayunbing? Is there a way to figure out what the latent representation semantic means? Actually, that is a good question, and usually no. So you can actually try to disentangle the latent space. For example, like you want the first dimension to represent whether it's exactly written here, like whether it has a long hair or short hair, and second dimension whether it has a mustache or you can try to enforce that by training with like contrastive learning samples between like images with long hair and images with short hair. You could somehow manipulate the latent space, but it doesn't completely guarantee that. Even if you do that, it doesn't guarantee. I mean, it's very likely that your latent space will represent long hair if you do that, but it doesn't completely guarantee. And usually, if you just train by cross entropy loss, then there is no guarantee at all that your latent space will be interpretable. So this completely leads to the XAI then, and the latent space disentangling. Questions from Cedric Caruso. Is there any property forcing the four-dimensional example to be an orthogonal space? Actually not. So the reason that I just drew this is completely just for your instructional purposes. Doesn't guarantee that the four-dimensional space would be, orthogonal space. I mean, actually, the four-dimensional space could be, I mean, you can represent, as long as there's four-dimensional space, you can always find a four-dimension, like, if you have this, then there's obviously four orthogonal, like 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. You can always find these four bases, but there's no guarantee that there will be sample that exactly follows that orthogonal basis. Like even if you map all your entire data to the four-dimensional space, there is no guarantee that you'll see a sample mapped to this, right? And another question from Nalfal: does the latent space dimension need to have lesser number of dimensions than the previous layer? Actually, that is a very good question. So this leads to a little bit more in-depth discussion about the latent space. But as you said, it could be, actually, the latent space could be larger. For example, this could be totally 1,000 dimensional space than 784. And the reason that I'm using four-dimensional space is, again, for the sake of the argument that you can compress images, which lives in the 784 dimension. You can compress the images into lower dimensional space and still get a good performance. Because if you think about it, classifying whether a given image is a man or a woman probably doesn't require the entire 784 dimensional space. It could be maybe four-dimensional space would be enough to, extract the essence of the image and then decide whether it's a man or a woman. So that is why, for the sake of the argument, I'm actually using four-dimensional space. But as you said, you can totally expand the dimensionality to 1,000 dimension. For example, it could be 784, and then blown up into 1,000 dimension, and then one dimension for the final classification. You can totally do this. And actually, classical MLP, multilayer perceptron, actually often uses a larger sized hidden layer than the input size, because that would give the model a more power, more capacity to learn more complex function, right? So the answer is no, it doesn't have to be always that the latent spaces has a smaller dimensionality than the input space. I'm just using it for the sake of the argument. Hopefully that makes sense. How can you define good representation? Actually, that's a very philosophical question. So how do we define good representation? Actually, a good representation is whatever representation that gives you the lowest loss or the highest performance possible, right? So that could be a little bit terse. So let me rephrase that. Whatever you learn here should be whatever space, whatever latent representation you learn in here should be such that it gives you the maximum classification accuracy. Then we can say that is a good representation. And when I say good classification accuracy, I mean test accuracy, not the training accuracy, because you can optimize your model until you get like 100% training accuracy and then overfit, and then your test accuracy would be terrible, right? I'm not talking about that. I'm talking about a nice latent representation will be whatever representation that gives a good generalization performance on your test distribution. 혹시 이해되실까요? 그러니까 좋은 latent representation이 뭐냐? 좋은 representation이 뭐냐는 건 결국 우리의 latent representation은 우리가 지정하는 로스 펑션에 의해서 배우기 때문에 우리가 지정한 로스 펑션에 의해서 지정하는 로스 펑션에서 배우기 때문에 로스를 떨어뜨리는 latent representation이 곧 좋은 latent representation이다라고 할 수 있는 거죠. 논리적으로. 그리고 그 로스를 떨어뜨린다는 게 단지 트레이닝 로스가 중요한 게 아니라 트레이닝 로스는 학습을 그냥 계속 시키면은 모델 사이즈 키워가지고 학습시키면은 100%를 찍을 수 있으니까 이론적으로. 그러니까 그게 아니라 테스트 퍼포먼스가 좋은 latent representation이 곧 좋은 representation이다라고 얘기할 수 있다는 겁니다. 네, 좋습니다. Already a discussion is going on between students. That's a very good thing. So Cecilia, I might be a little lost. Why is it beneficial to represent images as a point in a lower dimensional space instead of using the original pixel value? Actually, that's where we can discuss where this visualization can really help you. So the question, I'm hoping that the question is, why can't we just use 784 dimension and then directly classify into a man or a female, a man or a woman, right? Just like logistic regression without any hidden layer. Why can't we do that? If I interpreted the question correctly. So the reason that we need a hidden representation or latent space, whichever dimensional, whatever dimensionality it has, it could be 4 dimension, it could be 100 dimension, it could be 1000 dimension. That's actually kind of beside the point. The reason that we need a latent representation, we'll see in a minute. And we only need important info, not all the images, like we don't need background. Actually, that's a good point, but let me actually go to a very nice representation. This could actually take some time, but if you can grasp this concept today, that would be enough. So if you go to this Colas blog, actually there's a link there, right? Link in the material today. So if you can view it whenever you want. So let's assume that in a two-dimensional space, so your input is 2D, and all the samples, all the dots on the blue line is class 1, and all the samples on the red line is class 2. So it's a classification problem. Let me see the question from Aldo. Doesn't universal approximation says that we can in theory classify from 784 dimension with an arbitrary large layer? I'm guessing that as long as you have a sufficiently large hidden layer, then you can classify anything. That is true. So you need at least one, as Kim Tae-won says, you need at least one hidden layer to apply your universal approximation theorem. Right. Okay. Back to the sample at hand. So it's a classification problem, binary classification problem. So let me see if I can annotate. Okay, I get it. All right. So right. So one sample belongs to this blue line, another sample belongs to the red line, and what we would like to do is we want to classify between the two. And as you can see in the right here, as you can see here, it is impossible to perfectly classify the two because you can see that there are a certain region. All right, it's a little bit inconvenient to switch between the mouse mode and the draw mode. So here, I'm sorry, here and here, there are two sides, two corners where the sample from the second class it belongs to the region, which is this region here, region of the first class. So there's a decision boundary. There's a decision boundary right here, which is probably the optimal decision boundary, right? If we are drawing a linear decision boundary, then this is probably the best we can do. And even so, even with the best decision boundary, linear decision boundary, there are two corners here and here where we are making we're doing a misclassification, and also here we're doing a misclassification. So because it's the given sample, the given data distribution is impossible to begin with to perfectly classify with a linear decision boundary. So that's a like impossible task to begin with. So what we would like to do is we would like to draw some nonlinear decision boundary that looks like this, right? If this is our decision boundary, then we can perfectly classify between the red line and the blue line. That's what we want to do. What we want to do. So that's where the latent representation comes in. So as long as as long as there's no hidden layer. Actually, there should be only one one output neuron, because we're doing a binary classification between the red line and the blue line, right? So we don't need two output neurons. We only need one output neuron. But so let's forget about this one. And if we don't have a hidden layer, then you have a linear decision boundary. All you can do is always draw a linear decision boundary, something like this, or this, or this. Like, this is the best you can do. But with the introduction of the hidden layer, then you can start drawing a nonlinear decision boundary. Moving on. So yeah, right here, exactly here, we want to draw some nonlinear decision boundary that will give us a perfect classification between the two. And the important thing is, as you can see here in this image, what's happening, if you only focus on this part, and you can just forget about this part. If you only focus on this part, then the output here is determined by the input from the hidden layer. Actually, the output of the hidden layer. You remember last time in the previous session, we had Z and A, right? The input to the hidden layer and the output from the hidden layer, right? So we have the output from the hidden layer, A1, A2, A3, A4, and these A vector, A1, 2, 3, 4, this is this 1, 2, 3, 4. This is the input to the final output neuron. And if you only look at this part, you forget about this part. If you only look at this part, then what's happening is the output here, this output neuron is drawing. There's a linear decision boundary between this guy and this guy. There's a linear relationship between the two. Just like where we talked about, here. Oh, sorry, here. Without the hidden layer, there's a linear decision boundary between the input and the output right here. Just like that, right here in the hidden layer and between the hidden layer and the output, there's a linear decision boundary that's going on between when you view hidden layer output as the input to the output neuron. So that's why you can draw a image like this. So in the perspective of the output neuron, all it's doing is drawing a linear decision boundary given the output from the hidden layer, and the output from the hidden layer is warped. You can see the space is warped, right? It doesn't have a nice little grid, grid like this, there's a square grid everywhere, but now the space is warped. And the reason that it's warped is because we have a nonlinear activation function in the hidden layer. And you can see that the nonlinear activation function used in this function here is probably sigmoid, because you can see that the space is warped in a kind of an S shape, like here, like this. So you can see that, probably the sigmoid or 10H, kind of like an S-shaped, sigmoid shaped output nonlinear output function is used in the output activation function here, in the right here. So what's happening is because we cannot draw a linear decision boundary that perfectly classifies between the two, like this, we can't do that. We actually instead warp the space in the hidden layer. We warp the space in the hidden layer so that in the final layer, you can draw a linear decision boundary between the two. Now it's linear. Now these two samples, the blue line and the red line, are linearly separable because the space is warped, space is distorted. And now we can draw a linear decision boundary to perfectly classify between the two. And that is the power of the hidden layer. That is the power of the hidden layer. Hopefully that makes sense, okay? Does it make sense? That is the reason why we need a latent or hidden layer, actually. So that is why we need a hidden layer, because we want to warp the space into a linearly separable state as much as possible, so that the final layer, which is always just a final layer, is always just a logistic regression. As I said in the previous session, the final layer, like if you look at this part, let me clear things up. If you look at this part, this is just a logistic regression. The final layer is always just a logistic regression, but we want to make the final layer linearly separable, and that's why we need a hidden layer. So this becomes our latent space. And I think there's a very nice visualization. There's a continuous transformation of the input space, like this. And at some point, you'll start to see a nonlinear, like right here, right now. Now you're seeing a nonlinear transformation of the space. So this is linear, like rotation, expansion, compression of the grid space is all linear operation. 다 선형 변환이죠. 선형대수를 생각해 보시면, if you think about your linear algebra, multiplying a matrix to a input vector is basically, warping, transforming the space linearly. And this rotation, expansion, compression, and translation, 이렇게 선형 변환하는 게 다 이렇게 옆으로 움직이고 위로 움직이고 회전하고 이런 것들이 다 선형 변환이잖아요. So all those are just linear transformation, and linear transformation would not be sufficient to draw a linear decision boundary like this. You need to be able to warp the space non-linearly, like right here, like nonlinear transformation. And this again kind of seems like a sigmoid nonlinear activation function, right? So that's what's happening. And you can see that this is not just one hidden layer. This is actually like a series of hidden layers to make a sequence of transformation to the space, because you're like you're rotating, you're translating, you're expanding, and you're warping. So there's like a series of space transformation going on. So there's also a very nice picture here. If you have an even more challenging data distribution, not just like here. This is a little bit challenging, but you can still get a good performance out of a linear decision boundary. You only have like a slight errors here and here and here. But if you look at a spiral, like this cannot be, there's no linear decision boundary that will give you a good performance. But if you start transforming your space like this in a series of transformations, so there's probably like multiple hidden layers going on, like multiple hidden layers. Like there's input space, like actually the input space is two-dimensional. So input space, and there's like 1, 2, 3, 4, 5 hidden layers. And then after that, we draw a final linear decision boundary. And like here. Well, this is already linearly separable. Like, right, yeah. With this space, you can draw a linear decision boundary. Here, you cannot. In the original space, you cannot. So you can see a very, very harsh distortion, very severe distortion of the space is going on, because the original given data distribution was so challenging because it was a spiral. You need to severely manipulate the space so that it becomes finally linearly separable. So you can see the final space is nothing like the original space. The grid is completely warped. Questions from Soyeon Lee. So what we do during training model is that we warp the space to classify well. Exactly. In the classification setup, yes. But if we're doing regression, then we would be warping the space to do a regression well. Whatever task you have, could be translation, could be image style transfer, it could be ChatGPT, whatever task you have. All we do with deep neural network is we're continuously warping the space to do the final task well. And question from 선호안. 그러면 어떤 non-linear 방법을 어플라이 해야 돼? 그거는 이제 요즘 거의 정형화돼 있죠. 보통 이제 렐류, 뭐 프렐류, 뭐 셀류, 겔류 뭐 이런 거를 이제 많이 쓰는데 이제 시그모이드랑 이제 탄H 같은 건 이제 예전에 쓰던 방법이고 90년대 뭐 2000년대까지 2010년대 중반부터는 이제 렐류가 나오기 시작하면서 그때부터 백프랍이 훨씬 잘 되게 되면서 이제 거의 뭐 그런 뭐 거의 뭐 이렇게 그 몇 가지 안에서 정해지는 것 같습니다. 어떤 액티베이션 펑션을 쓸지는. So the question was, what kind of nonlinear activation function should we use from Tunnel? And my answer is that usually these days, I think it boils down to one of a few choices, few options, which is ReLU, PrelU, GALU, SALU, or Swish, or usually those functions. I think there was a question from Suhyun. When we try to compress representation into a smaller dimension, what is the choice of dimension size? And how do we find the good dimensions? Actually, that's all hyperparameter. How, given your given task, given your task and your data size, you should be able to guess a good size for your hidden layer. And you can actually choose. You can always explore your hyperparameter choice by setting a validation set. You have a training set and a validation set, and you can keep trying out different sized hidden layer and see which one gives you the maximum validation performance. And then you choose that size and then train it. And then you do one final test performance evaluation. Question from Chonghyunju. Does this distorting process always guarantee the linear boundary? Actually, no. Of course not. There's a very good question, which is right below here. If your data distribution in the original space is already too challenging, then no matter what kind of distortion you do, it wouldn't give you a linear solution. Like here, no matter what you do, it's already the two classes are too intertwined to solve this in a linear format, in a linear manner. Question from 충인님. 시그모이드는 찌그러지는 S커브를 나타내 공간이 변화가면 렐류 어떤 식으로 공간이 변하나요? 렐류는 그 네거티브 쪽을 다 버려버리잖아요. So this is sigmoid function looks like this, and tanh looks like this. ReLU looks, oops, this is a bad drawing. ReLU looks like this, right? So it means that all your negative values would be dropped off and it'll all be zero. So I guess, I don't know. That's a good question. As long as your input values all live in the positive side, then there will be no distortion in the space. But if it all lives in the negative side, then it will be completely collapsed into a dot because they will all go to zero. It's always zero, right? In the negative side, it all go to zero. So if, for example, if your input is completely negative, then it'll just collapse into a single dot, which is zero all the time. 0, 0, 0, 0, 0, right? So you're actually collapsing this space, but this would be an extreme example where all inputs all your input dimension would be a negative value. And the next question, ReLU가 다른 액티베이션 방식을 우수한 이유가 있는데, that actually, I think we might want to speed things up a little bit. So I'm gonna answer that question later. 명원님 질문 나중에 답을 드릴게요. Roka, but also different shape of the boundary is related to the hidden layer training model, right? Yeah, exactly. Yeah. So your linear decision boundary would look different based on your hidden dimension and your final latent representation. Cedric, for the current example on the screen spiral, would it be possible to use polar coordinate? Actually, I think that's a little bit beside the point that I'm trying to make. So this is using Cartesian coordinate. If you use polar coordinate, that might make a different representation of the input space, and then that might become linearly separate. I don't know. You could use polar coordinate and see if that will make this spiral thing linearly separate. That's a good question there. ReLU's distortion of the latent space reference. Okay, so 안영진 님이 이제 ReLU가 어떻게 latent space를 월핑하는지 페이퍼를 하나 레퍼를 해줬으니까 그걸 보시면 좋을 것 같습니다. 감사합니다. Right, there are a lot of, okay, so from Juncha, for ReLU, if I remember correctly, you should cut half of your feature space into two regions a combination of regions. If you have a lot of them, you should be able to arbitrarily represent any space within reason. Sure, yeah, that's a good point. Then disentangling various features in a generative model can also be thought of as warping dimensions. I mean, everything that we do is with deep neural networks, or deep learning, is about warping the space. And actually, it's not just warping, but we're actually expanding or compressing the space as well. So it's kind of hard to tell what's happening inside the generative model, such as ChatGPT, because it's so large and has such a lot. It has a lot of tokens because you're putting a sentence into it. There's a lot of words in it. So, for example, if your input is like 10 words, then there are 10 latent representations all going on. So it's kind of hard to see what's going on especially with the transform, because it's all about attention in the transformer. So, but you can assume that everything that we do in deep learning is about learning a well-behaved latent representation to do whatever task we want. 액티베이션 펑션을 밸류를 적용하면 네거티브 값을 버려버리는 이에 따른 부작용 해결 방안이 있는 건가? You might want to check out leak value를 네, 뭐 학생분들이 이제 다 서로 잘 답을 해주고 계시네요. There are some variants where your value function allows a slight negative values like this. You allow a small negative value, and that would improve your performance. And I mean, yeah, there's a lot of variants of value. Right. So in this case, where this is so intertwined, you cannot solve this by non-linearly warping the space. In this case, what can you do? Question. So, right. Okay. So already that was a really fast answer. So yeah, we can map into higher dimension. Actually, this is kind of a given answer, because right below there's already a answer there. This was kind of a given question. But anyway, so I think there was we should send them to higher dimension, right? Right, okay. So, for example, like this guy, how can I? Right, this guy. So here, these two are completely inseparable. Even with nonlinear decision boundary, for example, even if you draw a nonlinear decision boundary, this is inseparable, because the only way to completely perfectly classify between the two is drawing actually a circle like this. But which wouldn't be possible with just two-dimensional space, right? So that's why we need to send it to a higher dimension, and that there is a very nice picture. Very nice picture right here. So as soon as we send it to a three-dimensional space instead of two, so all these warping and distortion, they were all doing within this two-dimensional space constraint. All the, it's still two-dimensional space, right? We're not sending it to one-dimensional, three-dimensional, four-dimensional. It's still two-dimensional space. But here, now we're finally using another dimension, the third dimension, to detach the red ones from the blue ones. So now you can draw a linear decision boundary between the two regions right here. Actually, it would be hyperplane. So there will be like a plane like this. Then on the one side of the hyperplane, all the red ones would live on the top side, and all the blue ones live on the bottom side of the hyperplane. Now it's completely separable. So just by introducing one more dimension, we're actually making a linearly unseparable training samples into linearly separable training samples. So that is this. So you can kind of think of this as in the framework of overfitting, underfitting framework. So if you try to draw a linear, if you try to use just two-dimensional space, two-dimensional function to draw a linear decision boundary, then you would be underfitting, because you cannot solve this task by drawing a linear decision boundary. So when your function is underfitting, when your classifier is underfitting, what are the solutions that we can do? Which was increasing the power of your model, or actually introducing more features, right? So in this case, what we're doing is we're introducing more features. We're introducing one more dimension, which is another feature, and then this becomes linearly separable. So now it's perfectly, it's not underfitting, and in this case, it's not overfitting as well. So we're doing the right amount, we're using the right amount of power. Right, this is another example here. Yeah, and there's like a good description of the latent space and, you know, more advanced mathematical stuff. So if you're interested, you can read the remainder of this very nice blog. Question, comment from Junchanim. Alternative characterization, but equivalent result. A hidden layer with a higher neuron count can create a decision boundary with a number of pieces equal to its hidden size. So if you have enough pieces, you can create a circle. Actually, that's a nice intuition, but I'm not sure if everybody gets your point. But still a good comment, though. Right, moving back to the... Right. So hopefully this whole thing made a lot of sense to everybody who is, you know, just beginning their journey in the deep learning study. So very important stuff. What's happening in the hidden layers of your deep neural network is basically this series of distortion. And again, as I said, this is only confined to two-dimensionality in all these transformations. We're just using the two-dimensional input. We're still, you know, like sticking to the two-dimensional hidden layer. So if you would draw, your neural network architecture, it would all look like this. So you're just keep sending your input to a two-dimensional hidden layers where there's like nonlinear activation function every time. So that's what's happening here. But as I said, you can actually use a three-dimensional, and then one-dimensional output. That's what's happening in here, right here. Okay, so back to the slides. I need to stop sharing and then go back to the slides screen. Okay, we've used up already 45 minutes for this. Was there a question? 그럼 디멘션을 계속 추가하면 결국은 지점만을 반드시 찾게 되나요? 이론적으로는 그렇습니다만 뭐 이제 항상 그런 건 아니고요. 그리고 그렇게 디멘션을 계속 추가하다 보면은 이제 반드시 오버피팅을 하게 되는 상황이 오게 됩니다. 그러니까 내가 트레이닝 샘플을 완벽하게 100% 성능을 그러니까 100%로 분류를 할 수 있을 때까지 계속 이제 히든 레이어를 넣어볼 수 있는데 이제 그게 그렇다고 해서 반드시 리니어 세퍼러블 하냐 꼭 그런 건 아니고 근데 이론적으로 그렇습니다만 이제 뭐 반드시 개런티 되는 건 아니고 그리고 계속 그렇게 히든 뉴런만 추가하다 보면 반드시 이제 그 펑션이 너무 커져가지고 오버피팅이 일어나게 됩니다. 네, 좋습니다. Alright, so your latent space is shaped by your loss function, as I said. So your loss function. So whatever you do, whether it's man-woman binary classification, whether it's iris classification, whether it's house price regression, word embedding, French translation, or ChatGPT, whatever, it's just shaping your latent space is shaped by your loss function or your task. And today, because we're learning autoencoders, we should talk about image compression. So autoencoders, autoencoder consists of encoder and decoder. So the encoding is the compression phase where you map your original 784 dimensional input into 4-dimensional space. And then, so this would be encoding or compression, 압축을 하는 거죠, compression. And then decoder, so there's encoder and decoder. So decoding phase is where you restore, you reconstruct the original space back to 784. So this will be decompression. 이제 압축하고 마치 뭐 ZIP 그걸로 이제 압축 해제를 하듯이, just like you zip your file you zip your file or unzip your file. This is the same thing. You zip your original input, original image into 4-dimensional space, and then you unzip it back to a 784-dimensional space, and hopefully your input and the output, your input and the output would look exactly the same. if your compression algorithm guarantees no information loss, then your input and output would look exactly the same. So the zip algorithm is lossless compression, right? And for the autoencoders, there's no guarantee such thing. There is no guarantee that it will be a lossless compression, but we'll talk about that. Right. So, and this four-dimensional space value here, the value that lives in the four-dimensional space or your latent space, we call them code or latent variable or latent representation. They all mean the same thing. So, right. So how do we train this latent space? And obviously we would need to use a proper loss function, right? So a very simple, very simple autoencoder, the simplest autoencoder could look like this. There's input here, which is 784 dimension, and your four-dimensional space here, and your output, 784. You only have one learnable matrix here, which is 784 by 4. This W1. We're gonna forget about the bias. So the W1 would be a matrix of the size 784 by 4, so that you can compress 784 dimension into 4 dimension, right? So we need to learn the parameters here, and also the decoder would be a transpose. Decoder would be transpose. So one side would be 4 and the other side would be 784, so that, and that would be the dimensionality of the W2, the W2 matrix, so that you can map your 4-dimensional input back to the 784 output. So we need to learn these two parameters, the W1 and W2, omitting the biases, the B1 and B2. So how do we learn this? So the encoder would look exactly like this. You have an input from the X, which is X belongs to the dimension of 784, and the W1 is as I said, is 784 by 4-dimensional space. So your output will be Z, which is Z lives in 4-dimensional space. And what happens in the decoding phase is you put your Z into here, this function, and then you would have your X prime as the output, which is, again, X prime is X and X prime all live in the 784 dimension. And hopefully, what kind of loss function should we use? Hopefully, it's that these two should be the same. Your input, X, and your output, prime, should look exactly the same. All the dimension, every single dimension should match. Every single dimension should match, right? All the 784 dimensions. So that's where we use a L2, a squared L2 loss function. So this is a very simple setup, right? And as for the F is a nonlinear activation function. It could be anything. It could be sigmoid, it could be tanh, it could be ReLU or preLU, whatever you want. It doesn't really matter. We're just abstracting it away into some nonlinear function F. Or even there could be no nonlinear function at all. Then it would decrease the power of your model, though. Right, and you can use multiple layers. This is just a single layer in the encoder side, single layer in the hidden decoder side, but you can use two layers, like, MLP on this multi-layer perceptron with not one hidden layer on the encoder side and the decoder side as well. And then that would be like a cascade of hidden layers. So you would have X as an input, and then, for example, W, this could be 784, this could be like 100, this could be 400, and then 784, right? Then your input would go through the 100-dimensional latent space first, and then this would go into here, and then this would be the 100-dimensional space would be compressed into 4-dimensional space, and the decoder side would be exactly the opposite. Your 4-dimensional space would be expanded to 100 first, and then the 100 will be expanded to 784. And by using a nonlinear hidden layer here and here, you're increasing the power of your encoder and decoder. Question from Sujin. Should this model always have a symmetrical structure? Actually, no, that's a good question. It doesn't have to be symmetrical. It's just, just standard practice. Because it would stand to good reason to go through the exactly opposite process as you've encoded. As you've encoded, you probably need the opposite process to decode it, like an inverse function. So that's why we, usually use a symmetrical structure, but it doesn't have to be symmetric structure. you can, for example, like you can even just remove this and then have only the hidden layer here and no hidden layer here, and still it might work with, like if your data is easy enough, then it might work. Or you can use one hidden layer here and two hidden layers here, and it would still work, Okay, cool. Right, so because we're compressing the original 784 into 4-dimensional space, there's an information bottleneck because we're severely compressing the original information into only a 4-dimensional channel. It would, like, if you think about a pipe, like a water pipe, then there's an input water pipe here, and then suddenly there's like a very narrow water pipe here, and then we're like this. So there's like a severe bottleneck here. And the only way to guarantee that you will get a good reconstruction performance is by storing only the most distinguishing valuable information of the given image in this space. So yeah, we need to pack all information into 4D. And the only way to guarantee that you will get a good reconstruction performance is by storing only the useful hidden features. Okay, let me expand that a little bit. So, for example, if your image, because we're compressing the images, if your image looks like, so this is 28 by 28, all images would look 28 by 28, 20 by 28. And if, for example, this guy has a hat, and this is a like a woman with long hair, and this is a guy with glasses, In this case, and let's say that, for example, the background is always like black. Like all pictures, all portraits of the people, they all have a similar structure, similar like semantics, similar background, similar pose, similar in the size of their head and body. In this case, then, if their background is always black, it doesn't make sense to store these black information into this precious 4-dimensional space, right? If all images have black background here, they are all the same. So you should not store this undistinguishing feature into these 4-dimensional space, because these black information can be just memorized by the encoder and decoder, because all images share the same feature all the time. So you can just memorize it in this W2, B2, W1, B1, right? Actually, usually probably W2 and B2, because you're decoding it, you're reconstructing it. So a lot of the part in this matrix, like some portion could be responsible for making this black background, right? And the only thing that you want to store in this 4-dimensional space is whether this guy has a hat, whether this girl has a long hair, or whether this guy has glasses on. Like, these are the distinguishing features of these images. So you want to store those distinguishing features that distinguish one image from another, one sample from another. That is what we call useful features. And we want to only store those information, the distinguishing features, into this 4-dimensional space, because this 4-dimensional space is so bottlenecked. You only store the most precious information in the 4-dimensional space. Does that make sense? 이게 다 되시는 거죠, 지금? 그러니까 모든 이미지가 다 똑같이 생겼으면 애초에 배울 게 없습니다. 그냥 모든 이미지가 다 똑같은 이미지면은 배울 게 없어요. 그냥 외우면 되잖아. 그냥 메모라이즈 하면 되잖아. 근데 이제 조금씩 살짝씩 틀리다. 살짝씩 다르다. 그럼 그 살짝씩 다른 거를 여기에 넣어야 됩니다. 여기. All right, so since there's no question, I'm guessing this was clearly conveyed to you guys. Right, so still consists of 4. Yeah, this is a kind of a auxiliary stuff. So the question is whether these 4-dimension is still interpretable. Like, can we interpret what this is? Like, oh, this is like long hair, this is glasses, this is makeup, this is long hair. Probably not. So if you think about the PCA, if this is a two-dimensional PCA, right? If you do a PCA with two dimensions in the two-dimensional space, and then find the principal components, like this could be your principal. This could be your first principal component. This could be your second principal component. Then if you look at the first principal component, this is kind of a combination, linear combination of this base and this base, right? So if this is long hair, and if this is mustache, then your first principal component is a linear combination of the two. So it's probably kind of unintuitive, like to trying to interpret what each dimension is. And this is PCA, and PCA is linear. It's a linear process, but autoencoder could easily be nonlinear process. So if you include like this nonlinear hidden layers, then your autoencoder becomes a nonlinear compression, right? So this would the meaning of each dimension of your latent space would be probably very unintuitive and uninterpretable. Questions. 그러면 오토엔코더 잘 사용하기 위해서 특정 클래스 사진을 이용해 삭습하는 게 가장 좋을까요? 강아지 사진이든 고양이 사진, 사람 사진은. 꼭 그런 건 아니죠. 오토엔코더의 특성이 이제 이렇다는 거고, 이제 여기를 이렇게 심각하게 쪼여 놓으면은 이제 인풋이 784인데 여기 가운데가 4면은 이제 심각하게 쪼여놨기 때문에 가장 그 디스팅귀싱한 피처만 뽑는다라는 그 특성이 이제 오토엔코더의 특성이고, 어떻게 사용하고 싶으신지는 이제 사용자 마음이죠. 난 이거를 인물 사진만 컴프레스하는데 쓰겠다. 그럼 그렇게 쓰시면 되고, 나는 이걸 모든 사진을 컴프레스하는데 쓰겠다. 그럼 그렇게 쓰셔도 되고. 근데 그러려면 이제 모델이 굉장히 빵빵하게 커야겠죠. 모든 사진을 다 이제 어떤 레이턴 스페이스에 이제 그 우겨 넣으려면 일단 4디멘션은 턱없이 부족할 테고요. If you have some pictures that have different backgrounds, say one person has flower and the other has sky, still background doesn't matter. What should we do? No, background does matter then. So background does matter because we're trying to reconstruct. What we want to do is we want to reconstruct, but first we want to compress and decompress. So the loss function is a reconstruction function. So if every person has a distinguishing background features, then that needs to be encoded into the space so that we can do a lossless lossless reconstruction as possible. Right, I need to move on because we've already used up 1 hour. So I'm gonna answer the questions after the class. 정원님, 내가 몇 개 건너뛴 건가 본데요. 네, 하여튼 네, I'm gonna answer all the other questions after 12 o'clock. All right, so there's a very nice comparison between autoencoders and PCA. So as I said, if you learn PCA in your linear algebra class or like basic introductory machine learning class, PCA, the objective function of the PCA is maximizing the variance between each samples, right? So that is kind of the same as minimizing the reconstruction loss. Maximizing the variance and minimizing the reconstruction loss is semantically the same thing, because as I said, if you want to perfectly reconstruct your loss for every single sample, then you need to memorize the distinguishing features of each sample, right? If every sample is exactly the same, then you don't need to memorize, you don't need to like store anything. You can just memorize. If there's no variance, like this, like here, like, oops, what happened? Right here. So these are the background and the body part and the shape of the head. They're all constant. There is no variance between the samples. The variance between the samples is the hat, the long hair, and the glasses. And these varying this varying feature is the one that you need to memorize, one that you need to focus on. And that's what PCA does by maximizing variance. And that's what autoencoder does by minimizing the reconstruction loss. So those two are semantically the same thing. But the PCA is linear transformation. Autoencoder is may very well be nonlinear transformation. And PCA, you obtain the same number of principal components as your input dimension, but using autoencoder, you actually need to predetermine the size of your hidden layer. I'm sorry, the size of your latent space. In our example, it was 4, but it could be 100, it could be 200, whichever kdim you want. So, and for PCA, in order to use a higher dimensional space, for example, like in the concentric circle example, we needed to send it to a higher dimensional space to make it, linearly separable, right? If we want to do the same thing, kind of the same thing with PCA, then you need to use something called like kernel PCA. But in autoencoder, you can easily map your input to higher dimensional space. All you need to do is just increase the size of your hidden layer to, for example, like 1000. Like input is 784, 1000, then you're increasing the size of you're increasing your the representation of your input, which would be kind of unnecessary if you think about why we use autoencoder, which is to compress. But if you use higher dimension, like larger dimension in the latent space, then that wouldn't be compressing anymore. Right here, like what would happen? Oh, actually, yeah, if this is 784 and this is higher dimension, then and we are using MSE laws, like unlike I think actually, yeah, MSE this was the typical MSE laws. If we use a higher dimensional space, then what would happen to the MSE laws? MSE can be very low. Actually, the theoretical answer would be 0. It becomes identity function. Actually, that's a good point. If it becomes an identity function, it's possible that it becomes an identity function, which would amount up to the reconstruction error being 0. Identity matrix, not identity matrix, because there are 2 matrices here, right? Yeah, the answer is obviously 0. And in that, so as I said, if you think about the motivation of autoencoder, which is to compress and decompress, then using higher dimension would not make much sense. But if we have time, we can talk about sparse autoencoders. That is where higher dimensionality kind of makes sense. But since we're already 1134, we probably won't be able to cover that. Right, so the training process. So maybe we can speed things up a little bit here. The reason that I'm talking about training process is because there could be some newcomers who have no experience in machine learning, or specifically in deep learning, because deep learning's training process is a little bit different from, like, for example, like SVMs or random forest or logistic regression. Because for example, in SVM, you have a guarantee that you run as long as you want until you have like some gap between your objective function and your current status, then you're like good enough to go. So, but in neural network, there's no guarantee that how long you should train your model, and that's where we said that training set and validation set and test set is required to see when you want to stop your training process, right? So training neural networks usually boils down to these 6 steps. Splitting your data into training, validation, and test, obviously, and then loading the data, and then defining a model. You need to always define your model. It could be RNN, CNN, image classification, autoencoder, translation, whichever you want. You need to define your model, this is where you write your PyTorch code. And then obviously you need to define your loss, and then you need to define your optimizer, O. So optimizer being like, we only talked about the optimizer being stochastic gradient descent, SGD, which is the foundation of modern deep learning. But there's way more advanced optimizers such as Atom W, Atom X. Like, there's a lot of different optimizers these days, and you can choose whichever seems most appealing to you, or whichever gives you the most, like, good performance. So you need to define your optimizer, and then you start your training loop. You train. We'll talk about this training loop, and then after you've done your training, that is when you evaluate your best model M on the test set only once. You don't use test set during training loop. You don't use your test set on the training loop. You only use your test set after you finalize your model, and then you want to evaluate its test performance. I've said this multiple times, right? Right. So we'll take a look at it one by one. So splitting the training, validation, test set, you can usually use sklearn's train test split. We already talked about this in the self-check the self-check assignment that I posted on Classroom, right? And the ratio between train valid test is up to you, 811,622. If you have like gigantic amount of data, then probably you like 99 by 0.5 is also fine. And these days with ChatGPT, there's no train validation test at all, because you basically download the entire internet as your training set. So everything is used for training, and because the entire internet is the training data. So, and the test data is probably you chatting with ChatGPT is your test data. And loading the data. So you can, if your data is small enough, you can store your entire data into the memory, and when you're handling small data set. But if your data is so large, such as, again, GPT-3 or ChatGPT, then you need to stream your data from the disk, because you cannot fit it into your either your VRAM or especially your CPU RAM. If your data set is like few terabytes or few like petabytes or even exabytes, then you can store them on your memory, your RAM. So you need to store it in your hard disk and then stream it to your learning process. And usually, so you can use, if you're using like very like classical data sets such as Iris or like some translation data set or like Cypher 10 or like those stuff, then you can load them from PyTorch or Hugging Face. But if you have your own private data set, then you need to define these two classes to define the data set and then load it into your training process. And then defining a model, and usually we use modules from the Torch NN, and then defining loss, you can use cross entropy, MSE, L2 regulation, whichever loss you want to use. So that would be the model part. And the defining the optimizer part, as I said, you can use different, there are a lot of different options for optimizer. I think a couple of years ago, Atom was kind of like the go-to optimization algorithm. These days, I'm not sure what people usually use. Maybe it was Atom W or some other optimization algorithm. And you can find a lot of those algorithms in this path, torch.optim.star. And then you do the training loop, and then the training loop consists of this. So you repeat for n epochs. So epoch is, okay, so there's batches and epochs, and you should distinguish the two very clearly. So if, for example, your entire data set consists of 1,000 samples, this is your entire training set. And if your batch size is if your mini batch size is like 100, then you need to run 100 iterations, 100 iterations to go through the entire training samples once. So that would be one epoch. So one epoch consists of 100 iterations, 100 gradient, 100 parameter updates, or 100 mini batch iterations, right? So that is one epoch. So you can repeat this process for multiple epochs, which would be your hyperparameter, and repeat for k batches. That batch size is also your hyperparameter. So within each mini batch iteration, you fetch a random mini batch. You need to fetch random mini batch, because we're doing stochastic gradient descent. So your mini batch should be sampled IID, identically and independently identically distributed. So you need to randomly fetch your mini batch from, if you have 10,000 samples, you need to randomly select 100 samples every single time. And then you push those mini batch through your model M, you obtain your output, and then you calculate your loss, and then you use your O, the optimizer, to update your model's parameters. And that comprises one mini batch iteration, right? So you do that for k batches. So you do that for k batches. Like for example here, 100 iterations, and then you're done with one epoch. And after you've done with one epoch, you probably want to evaluate your model on a validation set. So this is where you occasionally check the validation performance of your model, so that you can know when to stop your training loop. And this validation set, you can evaluate the performance in terms of loss, validation loss, or validation accuracy, validation like F1 score, validation like blue score, whatever measure you want. And if that validation performance is so far the best, if best validation performance so far, because you're evaluating best validation performance every epoch. If it's the best performance so far, then you want to probably save your model M because it's the best one so far, and you want to use it later for evaluating the test performance. Right. Oh, actually, this is just explaining one step at a time. So fetch a random mini batch, and then using the data loader to fetch it, and then you push it through your model M, you obtain your Y prime, and then this is your loss speed. And you might also want to print out your C every once in a while. Or actually, there's like very good visualization tools these days, like 1DB, where you can monitor how your training process is going on, and hopefully your loss should be decreasing every single time, right? Then after that, you need to update your model's parameters. And first, you want to flush out the gradient from your previous mini batch iteration, because every mini batch iteration, you need to flush out the previous gradient information, and then you do a backprop from your loss value. You do a backprop, and then with the backprop, as I said, you do the backprop, and then you store your activation with the backprop. You can recursively calculate the delta value and then update your model parameter one layer at a time. According to the previous session, if you've listened to the previous session, you should exactly know what I'm talking about. By doing a backprop, you can recursively use the same delta on and on and on as you go down from one layer to another, and continue and sequentially updating the parameters for each layer, right? So that's what backprop does, and then you do a one update step, right? And then then we go on to the evaluation step. So after you've done one epoch, as I said, you want to evaluate your model on the validation set, and the validation set also consists of this mini batch iterations, because if your validation set is also too large to fit into a VRAM, then you need to split it into several mini batch iterations. For example, if your training set is 1,000, 10,000, and if your validation set is 1,000, and your mini batch size is 100, then even for the validation performance evaluation, you need to run 10 mini batch iterations, right? Because 1,000 divided by 100 is 10, right? So you need to do that, but you don't have to randomly sample in this validation performance, because you're not trying to update. You're not trying to learn, right? This is not a training loop. This is validation loop. This is an inference loop. So you don't need to randomly fetch mini batch. You can just sequentially fetch your mini batches in the validation performance loop, right? So please have a clear distinction between the two. There's a mini batch iteration for training loop and mini batch iteration for validation loop, and those two are different things. So you don't have to randomly fetch the mini batches. And so once you fetch the mini batch and you push it through the Y, you push it through your M, which is trained so far, and then you obtain Y prime, and then you evaluate your model performance you can do like MSC like here, or you can calculate the accuracy, you can calculate the blue score, whichever performance metric you want, and then calculate the validation performance. Right. And if your validation performance is the best one so far, then you want to, as I said, you might want to save your model you might want to save your model parameters. You can save it as a variable like this, or you can save it into your local hard drive like this. And then finally, you're evaluating on the test set. So after you've completed your training, you're evaluating your best model so far, best model in terms of validation performance, your best model so far on the test set. Only once. And the test set loop is exactly the same as a validation loop. You have actually it begins with loading the model. Actually, so there's a difference between the validation loop and the test loop. So in the test loop, you want to load your so far best model so far. So you want to, if you save your model as a variable, like this, then you can just simply load the variable like this. So M would be your model, and then loading the state dictionary is kind of like loading the parameters of your model. Or if you store your model in a local hard drive like this, then when doing the test run, you need to load your model parameter from the local hard drive. So once you've done that, once you've loaded your model, then you do the exactly same thing as the validation loop. You fetch the mini batch, it doesn't have to be random fetch, as I said, and then you push it through the M, and then you obtain Y prime, and then you calculate the model performance, and then you finally have the test performance, right? Accuracy, AURC, whichever you want. So that completes the training, the training process, the entire 6-step training process. And whatever we do in this course, it'll always follow this 6 steps more or less in the same manner. But as I said, if you think about modern deep learning architecture such as like ChatGPT, it doesn't go through this exactly, because first of all, it doesn't split data into training validation tests at all, and it doesn't do like okay, I'm not sure if it does occasional validation loop as well, because it's so large and it only goes through one epoch, because the entire internet data is so large. It takes up too much electricity to go through the entire internet data multiple epochs. So one epoch is probably like enough, So the modern deep learning, like gigantic large language models, deviate a little bit from this canonical 6-step training process, but all we do in this course is small enough, and it'll always most likely stick to this 6-step training process. Or there was a question already answered. If many batch randomly selected, there could be possibility that a data have not been being selected at all. That's a good point. Or a data selected many times through. But if you do it enough number of times, then it'll actually be truly IID. A mini batch should be selected without replacement, so each mini batch is chosen once. Actually, that is a good trick, selecting mini batch samples without replacement, so that one single epoch would go through all the samples in the training set without missing anything is a good strategy. It's a good trick. But if you think about running your epoch infinite number of times, like 100 epochs or 1,000 epochs or 10,000 epochs, then even without selecting without replacement, even without that kind of trick, you will asymptotically hit all the samples in a uniform manner anyway. But that's asymptotically speaking. Right, so I think we have time to go through. Okay, we have only 10 more minutes to go through the visualization. So visualization. So once we've trained our autoencoder, and then we have trained our latent representation, it is reasonable to think that similar looking samples would have similar valued latent representation, as opposed to 5 here. Like 1, these 2 should go to these like neighborhood in the latent space. You can see that. But as opposed to like 1 and 5, they are completely different. Like these values, one, like this value, this value, this value, this value, like more or less the same, as opposed to this value, this value, this value, and this value, right? So this is what we would expect if a latent space is properly trained in the autoencoder by the autoencoder, using the autoencoder, right? So how do we know this? We can't go by one sample at a time and study their values and see if they actually look the same or not, right? We can't do that, right? So what we do is we can instead use a visualization. And for example, if your latent space was 2-dimension, not 4-dimension, but 2-dimension, then we can treat this as an X coordinate, this is a Y coordinate, and then draw the samples using the scatter plot in the 2D space, right? Like this. And this is actually borrowed from the actual a latent space that we're going to use in this Thursday. So this is a real sample. So you can see here that all the 1s are like embedded here, and the 3s are here, 2s are here, and like 7 and 4s and 5s are like all intertwined. So it's not this autoencoder is not really clearly distinguishing between different digits, but at least for like these ones and these ones. Well, actually 3 and 8 kind of look the same. So maybe this makes sense. Anyway, so if you want to visualize something, then you need to compress your input into a two-dimensional space, or maybe three-dimensional space. Like we can still view 3D, right? But if you're on, for example, here, then how do we further compress this into two-dimensional space? Because our latent space of the latent space of our autoencoder is four-dimensional, but we need to further downsize it into two-dimensional space so we can draw a scatter plot like this. So how do we do it? So there are, so we need additional dimension reduction from dim-z, when our case dim-z was 4, right? And dim-z to 2. So that we can plot it on a 2D plane. So what kind of algorithm can we use for further additional dimension reduction? So there are popular 3 algorithms, which is PCA, t-SNE, and UMAP. So PCA, everybody knows what PCA. Hopefully everybody knows what PCA is. PCA, you can choose the first 2 principal components. For example, if your dim-z, if your dim-z was 4, then your principal, there will be 4 principal components, and you can choose the first 2 principal components to visualize using scatter plot. So that is one way to do it. t-SNE is a little bit better. t-SNE is it's an algorithm for dimension reduction, and it respects the local structure of the original space. So for example, if in the original space, if 2 samples were in the vicinity, then in the reduced space, which is 2-dimensional, the same 2 samples would still be in the vicinity. So that is the characteristic of t-SNE. But it doesn't guarantee that the global structure would be well preserved. For example, in the original space, if 2 samples were far apart, then in the compressed space, in the 2-dimensional space, there's no guarantee that those 2 samples would be still far apart. It could be closer than before. It could be farther than before. There's no guarantee. UMAP is kind of a new thing. Actually, it's been around for like a couple of years now, several years. So it's not a new thing anymore. But still, like it's more recent than t-SNE. So UMAP is, again, it's a distance-based algorithm, and you can actually determine the hyperparameter to how much you want to respect the global structure of the original space. So it kind of preserves the original global structure a little bit better than t-SNE, and you can actually like control it, adjust it using a hyperparameter. So you can actually see a very nice comparison between the two, t-SNE and UMAP, using this web link here. So let me briefly give you guys a visualization. Sharing screen, give me a second. Like this here, yeah. Right, so there's a comparison between t-SNE and UMAP. So this is compressing colored MNIST. So colored MNIST is, actually, no, this is not colored MNIST, sorry. This is fashion MNIST. Fashion MNIST is kind of like the digit version of MNIST, but it has, like, you can see here, like, different kind of clothes and different kind of like shoes and like heels, pants, shirts, dresses. So that's what fashion MNIST is. And when you embed fashion MNIST into 2-dimensional space using UMAP and t-SNE, you can see that, for example, t-SNE is already doing a pretty good job, like all the shoes. I'm not sure if you can see it. Oops. Yeah. All the shoes are like in the vicinity. All the shoes are in the vicinity. And the pants are like, the shoes and the sandals, they're all in the vicinity. And well, how do you call this? The shirts? Yeah, shirts, pullovers, coats, they're all in the vicinity. And what are these? Handbags. Okay, so the bags are in the one vicinity. So you can see that t-SNE is already doing a pretty good job of disentangling between different categories of clothes or attires or fashion goods, right? But if you look at UMAP, it's way more disentangled. So here, for example, here, the shoes, sneakers, shoes, they are in the vicinity with like bags or what else? yeah, bags or what is this? This is dresses. Like, yeah, like, because as I said, teasing doesn't guarantee that the global structure will be well preserved. So it could be that even though shoes and dresses have no common feature at all, they could be located in a similar vicinity like this. But here, if you look at UMAP, all the shoes are way below down here. Like all the shoes are all here, and the bags are here, and the dresses are here. So they're completely just disentangled, and they're all live in their own neighborhood, completely segregated, right? So you can see that UMAP is a little bit better in preserving the global structure compared to TSNE. So that's what I was talking about, global structure and whatnot. Yeah, you can interact with UMAP and TSNE in this website. So it's a very informative website. So you can, if you have more time, you can read further down the material. Right, and I think we don't have time to go through. I think that's it with the visual. So you just need to remember three things: PCA, TSNE, UMAP, and usually you probably want to use either TSNE or UMAP when you want to visualize what you've learned in the latent space, right? And UMAP is probably it's better theoretically motivated. As I said, it gives you some guarantee about preserving global structure. So you might want to play with UMAP a little bit. The problem is that TSNE and PCA, they're all in scikit-learn. So you can use sklearn to just easily call their function. But UMAP, you need to install it using like conda install or pipe install, that kind of stuff. So it needs one more step, but you should definitely give it a try. Right, so I think we're out of time, so we don't have time to go through the autoencoder variants. So let me just very quickly go over the contents. So there is something called sparse autoencoder, which is that you want to derive a sparse representation of your original input. Sparse representation meaning that a lot of things are zeroed out. Like there are a lot of zeros here, and you only want to have a very small portion of your latent space to have non-zero value. And this is said to have better performance in downstream tasks such as classification. If you use like sparse autoencoder, then it's kind of like a regularization, because this is kind of like an information bottleneck, because even though this is larger, the latent space is larger than the original space, a lot of them are zeroed out, right? A lot of them are zeroed out. So this is kind of like another way of enforcing information bottleneck. And the loss function consists of reconstruction loss and on the additional sparsity inducing term, which can be like a KL divergence or just plain old L1 regularization. So that's sparse autoencoder. Not a lot of people use it these days. Denoising autoencoder is a little bit more popular. It was proposed back in 2008 or 9, like very, very long time ago. And again, this is kind of like, this is actually pretty relevant to this day, because what this does is corrupting the input. So you have the original input, and there's corrupted input. You can use like Gaussian blur or something like that. Corrupted input, and then using this corrupted input, you send it to a latent space, and then you want to reconstruct it. But while reconstructing, you want this to be the same as this guy, the uncorrupted original sample. So this is denoising. So this process is all denoising the corrupted sample. And the intuition behind this is that small amount of noise doesn't affect high level representation. So even if you put some noise here, you can still kind of see that this is digit 2, right? It doesn't hurt the high level semantics, right? So this kind of like this kind of like the low variance, this kind of noise is a low variance feature. So in terms of PCA, you don't need them. Like you don't need the low variance features, because it doesn't mess the high level semantic. So in that case, there's another connection with the PCA and the denoising autoencoder. So small amount of noise doesn't affect high level representation. So if you are able to learn a very robust autoencoder that is able to denoise the noise and then understand the high level semantic, then it will be beneficial for the downstream task. For example, again, classification. Yeah. So the autoencoder must learn useful features, not the small dots here, but only the useful patterns, which is the 2 here, to perform denoising. Right. So yeah, we talked about PCA. And yeah, the loss function is not between this guy and this guy. It's between this guy and this guy because we want to denoise the noisy latent representation into the original clean, crystal clear image, crystal clear sample. Right, okay, so this is it. And okay, exactly 12:02. So all right, so the regular session is over, and I'm going to stay a little bit more to answer to the questions that I skipped previously. So you can all leave any time you want. If you have other places to go, please feel free to leave whenever you want. 네, 감사합니다. 네. So question from 선재상님. Could you explain the meaning of downstream in classification regarding sparse autoencoder? So, for example, if you learn a very sparse representation like this, and then you can use, so the downstream task, when you want to do downstream task, this is basically it's a two-step process. First, you train sparse autoencoder. This is step one. Step two is you obtain latent sparse representation of all your training samples. So that is step two, and then step three is use those training samples, use those latent sparse representations for classification, for training a separate classifier. So does this make sense? 선재상님 혹시 뭐 나가셨나요? 잘 모르겠네. 네네, 이렇게 하시는 겁니다. 그러니까 이제 일단은 오토인코더를 학습을 하고 그 다음에 그걸 가지고 레이턴 스페이스를 배워놨기 때문에 그 레이턴 스페이스를 모든 샘플을 다 보내가지고 예를 들어서 내가 이제 원래 이미지가 784인데 내가 여기서 뭐 예를 들어서 뭐 100 스파스 오토인코더니까 뭐 사실 1000이어야겠지만 뭐 1000이라고 합시다. 1000 디멘션으로 이제 학습을 시켜놓고 놨으면 이제 모든 샘플을 다 1000 디멘션으로 보내놔요. 일단. 그래서 이제 그 1000 디멘션짜리 이미지를 이제 그 샘플을 가지고 이제 우리는 알 수가 없는 더 이상 뭐 알 수가 없겠죠. 어떻게 생겼는지. 우리가 783은 이제 우리가 눈으로 보고 이게 어떤 이미지인지 알 수 있는데 이게 1000이기 때문에 레이턴 스페이스 1000이기 때문에 우리가 알 수 없는 어떤 0으로 가득 찬 대부분 0으로 가득 찬 값으로 돼 있을 테고 그걸 이용해서 이제 또 다른 이 분류기를 학습을 하는 겁니다. 그럼 이제 그렇게 했을 때 오리지널 784로 분류기를 학습하는 것보다 이 레이턴 스페이스의 1000을 가지고 학습을 하는 게 성능이 더 좋을 수도 있다. 그 얘기입니다. Alright, and okay. 구수진님, in a general generative model, each hidden layer contains different features. Can it be interpreted as follows? Warping through a nonlinear function space enables disentanglement of features. The bottleneck size and the number of layers determine which feature and how much of each feature will be captured. Theoretically, that is true. So when you say that in the generative model, each hidden layer contains different features, that is kind of like it's an afterthought. So you don't intend your different hidden layers to contain different features. You just put a lot of layers and then to make your model powerful enough, and then you train it, and then after the training, you analyze each layer, and then it happens to be that each layer contains different features. So it's an after process. It's not a predetermined, it's not a planned design. It's just something that happened. It just so happened that it is true. And because it's an afterthought, just like you said in number one, warping through a nonlinear function space enables the thing. If it's helpful so if disentangling features is helpful for performing the task at hand, then it'll do it. But it doesn't guarantee that it'll always disentangle the features. 혹시 이해되시는 거죠? 그러니까 이 모델, 이 학습을 하고 나서 봤더니 각 레이어가 다 뭐 어떤 레이어는 이제 뭐 컬러를 담당하고 어떤 레이어 텍스처를 담당하더라. 그거는 그냥 그렇게 된 것뿐이에요. 그렇게 하는 게 내 태스크의 로스 펑션을 줄이는데 도움이 됐기 때문에 그렇게 학습이 된 거지. 그래, 그게 항상 그런 게 절대 아닙니다. 그냥 어쩌다 보니 그렇게 된 거예요. 어쩌다 보니. And the bottleneck size and the number of layers determine which feature and how much of each feature will be captured. 그렇긴 한데, 그러니까 테크니컬로 그렇긴 한데, 이제 내 태스크에 따라서 결국에는 레이트 스페이스 배우는 게 크게 다르진 않습니다. 결국에는 내 태스크, 뭐 이미지 분류를 하든, 뭐 트랜슬레이션 하든 뭘 하든 간에 어쨌든 결국엔 태스크가 중요한 거고, 그 태스크를 잘 하기 위해서 레이턴 스페이스가 배워지는 거기 때문에 레이턴 스페이스에서 뉴런 하나 더 하고 빼고, 뭐 레이어 하나 더 하고 빼고 이런 거가 이제 아주 큰 차이를 불러오진 않을 거다라는 얘기입니다. Okay, cool. And another question from 정상윤님. 오토엔코더의 선실함수를 MSC를 사용했는데 다른 경우 MSC가 한 L1 로스를 써도 됩니다. 사실 L1 로스를 써도 되고 만약에 내 오토엔코더가 이제 바이너리 인풋을만 담당한다. 그럼 뭐 크로스 엔트로피 로스를 써도 되고 꼭 뭐 MSC를 써야 되는 건 아닙니다. 답이 됐다고 생각하시고 제가 하나씩 다 위로 올라가면서 읽을 거라서 굳이 다시 질문 안 하셔도 되는데 그럼 이제 이도현님 거부터 보겠습니다. 질문을 붙여버려서 Which is more important, cosine similarity or Euclidean distance in visualization? Actually, that's a very technical question. I would have to look at the algorithms of T-SNE and UMAP to properly answer that because I'm not really sure their underlying algorithm, the T-SNE and UMAP. So if for example, if T-SNE, for example, normalizes the input values before doing some kind of like dimension reduction or compression, then obviously the cosine similarity would matter more than Euclidean distance because everything is normalized, right? But I'm not sure if either T-SNE or UMAP normalizes their input values. So sorry about that. Question two vector is similar means their cosine similarity is close to one or Euclidean. Actually, that is also a good question. So it all depends on whether your vectors are normalized or not. So if your vectors are normalized, the only thing that matters is cosine similarity. But because the distance would be, I mean, their maximum distance is capped. There's an upper bound. But if the vectors are not normalized, then it could be their Euclidean distance could be infinitely large or zero at the same. I mean, it could be as large as an infinite value, right? So it all depends on whether your vectors are normalized or not. But usually when you talk about two vectors being similar, we usually talk about cosine similarity. And in the same manner, I would say in the T-SNE or UMAP, again, cosine similarity would be a bit more accurate measure to determine whether the two vectors are similar or not. Does that make sense? 답이 되셨을까요? 네, 좋습니다. Let me see. So going up, which is more important. Okay, 됐고. Mini batches randomly. Yeah, I talked about that. Cecilia Nova, how can you determine an optimal number of epochs and batch size for a specific task? Is there a specific formula or is it just depending on each person and case? So the optimal number of epochs and batch size, nobody really knows, actually. That's a very good question. And researchers put a lot of time trying to determine the effect of what if I use large batch size? What if I use small batch size? Like people have spent a lot of time trying to determine the effect of the size of the batch size and how long we should run for how long number of epochs we should run the training loop. There's been a lot of research going on, but the answer is usually for the number of training epochs, you usually want to use a validation set so that you can early stop. You don't want to train for too long because then your model will overfit, right? So you want to always have a separate validation set, and then every once in a while you want to evaluate your model performance against the validation set. And as soon as your validation set starts dropping, then that is a sign of overfitting. So you should stop the training loop at that point. So that is usually the principle that is applied in general. And for the batch size, I would say higher batch size the better. Like you don't want to use too small batch size, like 2 or like 5 is a bad idea. At least like depending on, it all depends on which task you're doing with which data set, but usually like 32, 64, 128 is kind of like a good size, and probably larger the better. But again, if usually you are constrained by your VRAM, so you can't use arbitrarily large batch size. I'm not sure how large a batch size they used in ChatGPT, probably like tens of thousands or hundreds of thousands batch size. Otherwise, if you use a batch size of 64 and you want to go through the entire internet, it's going to take like millions of years. So probably they use a very, very large batch size. Let me see. Other questions? From Masanim, if we have some picture that have different backgrounds, still doesn't back. Okay, I answered that. From Cecilia, does the size of the bottleneck layer affect the quality of the encoded and decoded representation? Yes, actually, that is a very good point. The size of the bottleneck does affect the quality of the encode. If for example, we kept talking about the four-dimensional latent space, but that is actually too small because your input size is 784, and you're trying to squish that in and squeeze that into four-dimensional space, which is too small a bottleneck, informational bottleneck. So if you do that, then your output, your reconstructed image would look very blurry and very low resolution. So yeah, I would say that the size of the bottleneck would severely affect the quality of the reconstructed image. Question from 김현진님. 특징 추출이 분류가 목적인 데이터 레프레젠테이션과 복원이 목적인 디코더를 다르기도 한가? 오토엔코더는 사용 목적이 하나입니다. 리컨스트럭션이기 때문에 데이터 레프레젠테이션은 항상 비슷한 특성을 가지겠죠. 만약 똑같은 데이터셋을 쓴다면 똑같은 데이터셋과 똑같은 뭐 구조의 오토엔코더를 쓰면은 학습할 때마다 또 거의 비슷한 레이턴 레프레젠테이션이 얻어지겠죠. 근데 질문이 약간 좀 복잡해가지고 제가 잘 이해를 못하는데, 그 이제 레이턴 레프레젠테이션은 결국 우리가 어떤 이 목적을 위해서 학습을 하냐에 따라 결정됩니다. 내가 리컨스트럭션이니까 디컴프레션과 디컴프레션을 목적을 하냐, 분류를 목적을 하냐, 리그레션을 목적을 하냐에 따라서 다 레이턴 레프레젠테이션의 쉐입이 결정됩니다. Question from 허정원님. So the role of the autoencoder is making a latent vector. Actually, that is true. The role of the autoencoder is actually on the surface level, the role of the autoencoder is to compress and decompress. But then again, if you look at in a little more in depth, then that is exactly what you said, is to make a latent vector. But it's not just any latent vector. It's a latent vector that is optimal for preserving the most distinguishing features between each samples, just like PCA, but in a nonlinear manner. Hopefully that makes sense. I think there was a question way up there that I skipped regarding some ReLU-related question. 렐류가 다른 액티베이션 펑션보다 우수한 이유가 있나? 이거에 대해서 얘기를 안 했는데, 렐류가 다른 액티베이션 펑션보다 우수한 이유가 있나? 렐류는 다른 액티베이션 펑션들은, 이 그림을 좀 그려야 되는데, 다른 액티베이션 펑션들은 이제 시그모이드 생각하면은 이렇게 생겼고, 타니츠 생각하면은 이렇게 생겼잖아요. 그러면은 이게 양쪽 끝으로 갈수록 그레디언트가 거의 0에 가까워지거든요. 0, 0. 여기도 이제 여기도 0, 0. Actually, I should speak in English. So if you think about the nonlinear activation functions, sigmoid here, sigmoid, or tan h here, they all have, if you go to the either extreme, to here or here, here or here, you get to the point where the gradient of the function becomes nearly zero. So if your gradient becomes nearly zero, then it is not good. It's not a good sign for backpropagation, because then the lower layer wouldn't be able to receive a proper error signal because the gradient is nearly zero here and here and here. So if your values become large enough, then because of the properties of the sigmoid functions or tan h function, your gradient will soon become zero, and then that wouldn't be able to convey proper error signal to the lower layers in the backpropagation process. But ReLU doesn't have that problem. Because ReLU always has gradient of 1 in all regions as long as you stay in this part. And in this part, this is the nonlinear activation part. This is the 0 part. But as long as you're here, it'll always have the same gradient, which is 1. And that is why the error signals can be propagated properly to the lower layers during the backpropagation process. Does that make sense? 이게 이제 박명원 님이 해주셨던 질문입니다. Right, moving on to the new questions. 이동원님, 배치 사이즈 관련해서 여러 자료를 보면 이의 n승 숫자로 주로 설정한 특별한 이유가 있나요? 이진적인 컴퓨터 연산 구조 때문인가요? 제가 알기로는 이게 구글에서 이제 TPU를 만들 때 텐서 프로세싱 유닛 있죠? TPU, 그 GPU랑 비슷한 거. TPU를 만들 때 TPU가 이제 아키텍처 디자인이, 이제 이건 하드웨어 디자인 얘기인데, TPU의 그 아키텍처 디자인이 2의 승수로 처리를 해야지 굉장히 빠르다고 해서, 그때 이제 배치 사이즈랑 이런 것들을 다 2의 승수로 막 배치 사이즈도 그렇고, 뭐 예를 들어서 NLP를 한다 그러면 이제 시퀀스 랭스도, 트랜스포머 시퀀스 랭스도 막 512, 256, 1024 이런 식으로 다 2의 승수로 맞춰놓고 해야지 TPU를 맥시멈으로 이렇게 최고 효율로 돌릴 수 있다 그래서, 그때 이제 구글에 있는 사람들이 많이 그렇게들 조절을 했었습니다. 근데 이제 그게 뭐 다른 데로 퍼져나가는지 그것까지는 잘 모르겠지만, 적어도 구글에서는 이제 그렇게 해야지 TPU를 제대로 활용할 수 있었기 때문에 여러 가지 어떤 하이퍼 파라미터들을 다 2의 승수로 맞추고 있었어요. 요즘도 그런지는 잘 모르겠습니다. 그때도 이제 TPU가 뭐 이미 버전 2인가 3였기 때문에 지금 뭐 TPU 뭐 훨씬 나중 버전이라서 훨씬 더 플렉서블 할 수도 있겠죠. 김현진님 특정, 이 질문 제가 답 드린 거죠. GPU를 사용해도 저희들은 이해 승수로 배치 사이즈 설정을 할 필요, 네, 딱히 그럴 필요 없는 것 같은데, 잘 모르겠어요. 제가 이제 요즘 GPU 뭐 쿠다 아키텍처나 뭐 파이토치의 언더라잉 임플리멘테이션을 몰라가지고, 여전히 뭐 나름대로 파이토치나 쿠다 얘네들이 뭐 이해 승수에 조금 더 유리한 면이 있을 수도 있고 뭐 없을 수도 있는데, 그것까지는 제가 잘 모르겠습니다. 그건 한번 뭐 스택 오버플로우나 이런 데서 한번 살펴보시면 좋을 것 같네요. 한번 살펴보시고 클래스홈에 알려주시면은 다른 학우분들에게도 도움이 많이 될 것 같습니다. 예를 들어서 저는 예전에 박사 할 때, 2014년, 15년 할 때 이해승수 같은 거 하나도 안 썼었어요. 뭐 100, 200 이런 거 썼었는데, 뭐 혹시 모르죠. GPU 요즘 막 뭐 A100이나 A6000이나 이런 것들이 또 사실상 이제 게임을 위해서 나온 게 아니라 딥러닝을 위해서 나온 거잖아요. 그럼 이제 A100이나 이런 애들이 또 이해승수에 맞는 뭐 최적화된 아키텍처를 가지고 있을 수도 있기 때문에, 그런 거는 이제 그거 제가 잘 모르겠습니다. 허정원님, 그러면 오토인코더에서 인코더 부분만 사용하면 여러 태스크에 사용되는 레이턴 벡터를 만들 수 있나요? 바로 정확하게 맞습니다. 바로 정확하게 맞습니다. 오토인코더에서 오토인코더 학습한 다음에 인코더만 딱 띄워가지고 인코더만 딱 띄면 그건 사실상 레이턴 벡터 뭐 제너레이터라고 볼 수 있는 거죠. 이제 아무 샘플이나 내가 원하는 그 특정 레이턴 벡터를 보낼 수 있는 범용성을 가진 레이턴 벡터 제너레이터를 만들었다고 볼 수가 있습니다. 근데 이제 그게 여러 태스크에 항상 좋은 성능을 내냐, 그런 건 절대 아니고요. 보통은 이제 특정 태스크에 맞는 레이턴 스페이스를 만드는 게 좋습니다. 지금 오토인코더는 리컨스트럭션을 잘하는 레이턴 스페이스를 만들어 놓은 거기 때문에, 그 스페이스가 예를 들어서 분류든 뭐 번역이든 뭐 이미지 생성이든 이런 데 다 두루두루 좋을 거란 보장이 전혀 없어요. 그렇기 때문에 보통은 내가 하고 싶은 태스크에 맞는 특정 태스크에 맞는 레이턴 스페이스를 배우는 게 훨씬 더 유리합니다. 스파르시티가 중요한 이유는 뭐예요? 스파르시티가 중요한 이유는 사실상 스파르시티가 중요하다기보다는 그냥 이제 그렇게 마치 드롭아웃을 하듯이 일부러 이제 아주 많은 스페이스를 준비해 놓고 이제 그 특정 스페이스들 그 중에 뭐 예를 들어서 80% 90%는 랜덤한 확률로 이제 0으로 이렇게 끊어버리면 그게 사실상 레귤러라이제이션 하는 거랑 비슷한 효과를 가지기 때문에 훨씬 더 로버스트한 성능을 가지게 됩니다. 그러니까 이제 약한 아까 그 디노이징 오토엔코더처럼 이제 작은 노이즈에는 반응 안 하고 정말 하이 레벨 세만틱만 잘 잡는 그런 이제 로버스트한 레이턴 스페이스를 얻어질 거라 생각을 하고 이제 스파르시티 인듀싱 텀을 쓰는 거예요. 네, 다 답이 되셨으리라 생각을 합니다. Alright, any more question? 혹시 더 질문 있으실까요? 제가 다 답을 한 것 같은데요. 더 중요한 피처를 구분하기 위해서 네, 그렇죠. 더 중요한 피처라는 건 결국 더 개개의 샘플을 구분하기 쉬운 하이 베리언스 피처를 잘 뽑아내기 위해서 스팔시를 쓰든 디노이징을 쓰든 하는 거라 보시면 됩니다. 그게 사실 요즘에도 계속 쓰여요. 그 원리가 심클리어나 뭐 클립 같은 데서도 이제 이미지를 막 이미지 오그멘테이션 하잖아요. 그 셀프 슈퍼바이즈 러닝 할 때 이제 뭐 이미지 약간 돌리기도 하고 크라핑도 하고 뭐 약간 노이즈도 넣고 솔라라이제이션의 색깔도 약간 바꾸고 이런 식으로 살짝 바꿔가지고 그 학습을 하는데 그게 다 하이 레벨 세만틱을 잘 뽑기 위해서입니다. 좋습니다. 네, 아직도 무려 50분이나 계시네. 네. 더 질문 있으신가요? 없으시면 이 정도로 마무리하려고 합니다. All right, I think there are no more questions, so I'm going to end the session today. If you have more questions, you can always use class. All right, thank you guys very much. Thank you guys very much, and I'll see you guys. Actually, next Tuesday is regular class day, but next Thursday is actually the Chuseok day. So we'll talk about how we're going to proceed with that on class. All right. Thank you very much. All right. See you guys next week. Bye bye. Bye bye. 네, 감사합니다. 네, 감사합니다.